Okay, so let's go to the second half of section 1.1, and I'm going to call this number 3, right? And so this is, let's say this is, well, a little complicated graphs. Okay, again, I'm not going to spend a lot of time doing all kinds of functions, okay, because there are so many different types. We will talk about how to classify different functions in the next section. But let's say here's a function. Okay, what kind of function is this? Okay, first you can see this is a fraction, right? You have a numerator and a denominator. The numerator happens to be a linear first degree polynomial, and so is the denominator. Okay, and such a function is called a, anybody know? Rational function, all right? And so if you are to evaluate this, for instance, you could, of course, do that, right? Evaluate this at x is equal to, let's say, 3, 1, and -1, okay? Let's go ahead and do this. Well, that's pretty easy. All you have to do to evaluate, of course, is to plug in these numbers. When you plug in 3, you get, oh, sorry, let's just say 3. Okay, so this is going to be 9, it's 3 times 3, divided by 3 plus 1, that's 4. Okay, no problem, right? Evaluate this at 1. Okay, what do you get? That's going to be 3 over 1 plus 1, 2. Okay, how about evaluate this at -1? So that's going to be -3 over 0. You have a problem with this? Of course, you should have a problem with this, all right? And I should emphasize this, right? You never, ever want to show me this, okay? Because to see this 0 in the denominator, okay, I take this as an obscene gesture. This is something that you should not do in public. Make sure, you can do this in privately, but make sure you erase this and don't let anybody record you with such a bad behavior as writing a 0 in the denominator. Okay, you should not be doing this. Okay, in fact, I'm just going to erase this because I don't want to keep this on my record. Right, so I don't want to be accused of saying something something horrible. All right, so when you write, okay, f of -1, instead of writing that 0 in the denominator, you just say this is undefined. Okay, you don't want to say this is equal to undefined. You want to say it is undefined. So the function is not defined at -1. Oh yeah, some people write DNE to say does not exist. That would be okay too. All right, now the question is, do you know how to graph this? You may want to stop this video and pause it at this point and then try to graph this thing, okay? In fact, why don't you do that? All right, try to plot these points maybe, and then tell me what kind of function you can come up with, and I'll be right back. Okay, so you can start with the xy plane, which is what you normally do for these functions, and then you can start plotting points. Okay, we have already figured that when x is equal to 3, y is 9 over 4, which is what, 2.25. Okay, so it'll be somewhere here. Okay, and when x is 1, it's 3/2, which is 1.5. Okay, no problem here. Something happens when x is -1, and in fact, it's not defined, right? And what happens is, as x approaches -1, okay, maybe I should say this, as x approaches -1, okay, what's going to happen to the denominator? X plus 1 approaches 0, right? Either from positive or negative direction. All right, so that's something that you want to think about. And as this get closer and closer to 0, and the top does not go closer to 0 because as x approaches -1, the top becomes -3. So it approaches -3 over, or something close to -3 over a small number, very close to 0. And so that what happens is, as the denominator becomes close to 0, the value of the function gets closer to either positive or negative infinity, depending on whether it's approaching 0 from the positive side or the negative side. All right, so this is so far all we know. Okay, now what happens as x approaches infinity? And this is the kind of thing that we will study more carefully as we study calculus. But what happens is f of x is 3x over x plus 1, right? Okay. You can divide the top and the bottom. If x is not 0, or if x is not 0, you can divide the top and bottom by x. All right. And if you divide everything, every term by x, this is what you get. And of course, as x approaches infinity, this goes to 0, right? So that means not equal to, okay, but as x approaches infinity, this last thing approaches 0. So the whole thing approaches 3, okay? And this is what we know as, what do we know this as? As x approaches infinity, or actually for negative infinity as well, okay, the value of the function approaches 3. And so this is called a horizontal asymptote, right? And so you have this function like this. And by the way, let's calculate f of 0, okay? And you can see this is 0 over 1, so it's 0, right? So it gives you additional point like this. All right, and we know from just studying these rational functions, when you have a 3 points like this, you can pretty much graph the rest of this. And the rest of the graph would look like this. Now, like I said, this is a pretty difficult graph to function, to graph, not graph to function. And so if you can't do this right away, that's okay. I mean, when I look at this function right away, if somebody asks me, what does a graph look like? I'll say, give me 5 minutes, all right? So this is fine. And also, if you approach x from this side to -1, okay? So you're talking about points like, x is equal to -2, -1.1, -1.01, -1.001. This number, the denominator, will remain negative. And of course, the top will also be negative, right? And so negative over negative is positive. So from this side, the function will stay positive, all right? And we just know from analyzing different types of rational functions that the other side will be above this horizontal asymptote. And so the graph will be something like this. Okay. So again, you don't have to be able to graph these things instantly or very, very carefully, but just have an idea of what the graph should look like for different types of functions. All right. And also, you should be able to define or find the domain of these functions. Here, the domain is all except -1, right? The notation that you will be using, or the interval notation you'll be using, is that the domain is from -infinity to -1, open interval, union from -1 to infinity. Again, it is a nice polite way to say everyone is welcome except -1. Okay, so then let's go to the fourth item in section 1, which is increasing and decreasing functions. Okay, so if you have a function, and let's say we are considering this interval from a to b, right? And so you have a function. Let's say the function goes like this, a to b, right? And you want to say this function is increasing, right? Because it's obviously increasing. Okay, well, what do we mean by obviously increasing, right? So here's the definition, more technical definition. And this is, by the way, something I should tell you. As you study calculus, you are becoming more serious students, okay? And so that means you want to learn how to say things properly. Okay, so learn the precise mathematical language. All right, so we say f is increasing, okay, on this interval from a to b, okay, and you can see that, right? When what? If, okay, and what you want to do is anytime you go from a point to another point to the right, then the f is getting bigger, right? That's the point, right? So if whenever x1 is less than x2 on this interval, all right, so make sure that x1 is less than x2, then whenever x1 is less than x2, then f of x1 is less than f of x2. Okay, that is the precise definition, or this is a precise definition of function being increasing on the interval a and b. And of course, you can also define f is decreasing whenever, maybe I should say that too. All right. F is decreasing on AB if, now you may say, well, I want to switch both of these lines. Well, no, you can't do that. Okay. Decreasing means this. Here's A, here's B. Anytime, again, whenever x1 is less than x2, you want x1 to be still less than x2. But at this point, because you want the function to be decreasing, you want to say f of x1 is greater than f of x2. Okay, and so that is how you define increasing or decreasing. All right, let me give you an example. Can you give me an example of a function that is always increasing? F of x cubed, which looks like this. X, okay, right? These are always increasing, right? And f of x, of course, like negative x cubed. Of course, this is always decreasing, or negative x. Most functions are neither decreasing nor increasing. Oh, here's another important one. If you have a natural log of x or log of x, or e to the x, 10 to the x, all of these, okay, these are always increasing functions in their domains. All right. I have a couple more things to mention fairly quickly, a couple more concepts to talk about in section 1. And so let me go to number 5. I guess it's number 5, right? All right, so this is the algebra of functions. What do you mean by algebra? Do you know what algebra means? Algebra of functions. Yeah, the word algebra is actually from an Arabic, right? And it's the first couple of words in the title of a book about finding solutions to polynomial expressions. And so it's called algebra, blah, 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 whatever. Okay, I don't know the rest of the topic or the title in Arabic. But the word al is like the definite article, the, okay? So the book on something, something, something. And so that's where we get the word algebra. And it has to do with solving equations, not surprisingly. And things like binary operations. Now, what are binary operations? Binary operation is to take two elements of the set, like if you have the reals, okay, take two things, and binary means two, and produce one set, one element in the same set. Okay, so for instance, addition is a binary operation. When you take 3 and 5, you get 8 as the sum of 3 and 8. So that is a binary operation. So we define these binary operations like addition, subtraction, multiplication, and so on. And so that forms an algebraic structure. Okay, and that the word algebra has to do with the sum, difference, product, and so on. Okay, so we can define f. Okay, so let's say given f and g, two functions, we can perform these binary operations. So f of g, f plus g turns out to be a new function, which is what do you think f plus g, what do you think it's supposed to do? Okay, to x. Well, it's simply f of x plus g of x, assuming that these two numbers or two things can be added together. Now, I want to emphasize this very, very important concept here. You see two plus signs here, right? This and this. I want you to know these plus signs really don't mean the same thing. Okay? Because here, what are we doing? Here, we are adding functions, right? But here, whatever f of x is, I assume it's a real number. Here, we are adding real numbers, adding values. Okay, so theoretically, these could be two different additions defined in two different, universes or two different sets. And so it's not a big deal right now. And because we will be talking about real valued functions, it doesn't really matter. But I do want you to know here, we are defining how to add two functions, okay? Here, we are talking about the same addition that you have used since your elementary school days, right? So this is a new concept here. How do you add two functions to create another function? Well, the new function simply adds the values of those two functions at the same point x, right? Same thing here, f minus x, this is the difference of two functions. It is defined as the difference of the two values, f of x minus g of x. Not hard, right? Fg, a product of two functions, is obtained by multiplying f of g, f of x, and g of x. The quotient of two functions is simply f of x divided by g of x. So these are all easy. Oh, by the way, here, one disclaimer. We want to make sure that g of x is not equal to 0 at that x, right? So that's not too bad. Oops. All right. So, but one very, very important operation is this thing called the composition. Okay, and this will play a major role. And in fact, most functions that you will encounter in life and applications are composition functions. The composition is this thing called f of g. We have this circle, an empty circle in the middle, which means it's a composition, not the not the product here. All right, f of g of x. The way we define this is f is applied to g of x. Right. A warning here: you write f first and g next. But in reality, you are operating on x by g first and then f next. Okay, so this is very different, right? G followed by x by f. So g does its work first on x, and then it's followed by f. So here's the picture. You put x into this box called g first, and out comes g of x, okay? But that's thrown again into another box called f. And out comes f of g of x, right? And so that is a composition. Think of the composition as the big box that contains both of these, okay? G does its work first, and then f does it next. So this whole box is called f of g. Somebody in history of mathematics messed this up, okay? To write composition in this order, because we read from left to right, right? But in operation-wise, we do a right and then left. And so I wish we could go back and fix this problem, but that's what happens. All right, now let's say f means putting on your shoes, okay? G means put on socks, okay? And X are your feet. All right, so you take your feet and you put your socks on there, and then you put your shoes on top of it, right? F of G of X is going to be looking something natural and nice, okay? Hopefully, when you have your shoes on and you have your socks on, you have a pretty decent looking thing. All right, so that's okay. Now imagine you do G of f of x. So this will be like you take your feet, you put shoes on your feet, and then on top of it, you put your socks. Now this will look ridiculous, okay? This will look terrible. And you don't want to be walking around with the socks above or on top of or over your shoes, right? But this is what happens. So this is to say, f of g is not the same as g of f. And that's natural. I mean, that's obvious, right? Because the order in which you do things matter. Okay, so for instance, you open the door and you walk into the room. Okay, try to reverse that. And you try to walk into the room and then open the door. You are going to get hurt. So don't do that, right? So that, again, illustrates that the order matters. F of g is different from g of x. The f of g is different from g of f. All right, so let's say here's an example. Let f of x be 1 over x, and g of x be x squared plus 1 or something, right? What is f of g of x? Okay, well, all you have to do is to just write g of x. Okay, now what does f do? Okay, now again, here's the idea. Try to talk in English or whatever your native language is. Try to explain to me or to yourself, what does f do? What does g do? Okay, in your language or in English, what f does is to take the reciprocal of x, or to take 1 and divide that by x, right? That's what f does. F is basically the reciprocal function or the inverse function. G is the function that squares the input and add 1 to it, right? So when you do g first, g of x is this thing, x squared plus 1. Now, f is going to do its work on whatever the new input is, which is to take the reciprocal. So this is the correct answer, 1 over whatever is in the parentheses. Right? Now, g of f, remember, is different, typically different from f of g. F does its work first. So f does the x, and that becomes 1 over x. Now, g is going to square whatever you put in there and add 1 to it. You can simplify this to 1 over x squared plus 1. Okay, so again, it is different from f of g. And we'll talk more about the compositions. Compositions play a very important role as we study calculus, and so pay attention to that. All right, finally, the last thing I want to mention is something that is a nice tool. This is called the symmetry. All right, symmetry, what do we mean? Symmetry is like, some sort of a reflection or rotation or something, right? Okay, so let's think about, or let's take an example of a absolute value function. Like that, okay? What does it look like? Well, it comes in like this and goes out like this. So this part is the same as x. Y is equal to x. This part is the same as y is equal to negative x. Right? By the way, this is defined piecewise as x greater than, well, see, this is equal to x if x is greater than or equal to 0. Okay, and it's negative x if x is less than 0. Okay, hopefully you understand this. If x is equal to some negative number, negative of the negative number is positive. So basically what this is saying is, just remove that negative sign if x happens to be negative, and that is your absolute value function. Notice here, if you switch the left and right hand side here, it'll be the same function, right? So this is called an even function. And an even function is the function so that negative of x and the positive x, or the vice versa, it doesn't matter which one. So f of negative x is equal to f of x, and the symmetry is the left-right symmetry. All right, so left-right symmetry, which is nice. Okay, if you know the function's even, then just do the graph of one side, and then the other side will be symmetric. So you can use that. All right. Let's say you have this x cubed function. What does that look like? Well, it increases very quickly, and then 0 gets mapped to 0 again, and then this is a sort of a cool shape, right? And so this function is not even because f of negative x is not f of x. Actually, let's try to figure this out. What happens if you take the negative and cube it? Right? That's negative of x cubed. So this becomes negative of f of x. So this is called an odd function. And so this is rotation. The symmetry is a rotation by 180 degrees or pi. So if you switch this, turn this around, 180 degrees, or turn the sheet of paper and hold it upside down, it's going to look exactly the same. And so that is called an odd function, and it's symmetric with respect to the origin, by rotation by 180. Now, most functions are not odd and not even, right? If you have x, y is equal to x. Okay, which one is that? It's an odd function, okay? But if you just like add 1 to it or something, that's neither. Okay, y is equal to x squared. That's even. Okay, but if you do y is equal to x minus 2 squared, for instance, that's neither. Now, this function itself is going to be like this. You know, it's a parabola based our centered at 2, 0. This function is, okay, but it is not symmetric, right? I mean, it is symmetric with respect to this line, but not symmetric with respect to the WRT means with respect to. It's with respect to the y-axis. When the function is even, the symmetry is with respect to the y-axis, which is basically saying you can switch the left and the right-hand sides, and it would look the same. It's a reflection with respect to the y-axis, but here, yes, it is symmetric with respect to the line x is equal to 2, but not with respect to the y-axis. So this is neither. All right, we'll talk more about the different kinds of functions, but in the second section, we'll study specific classes of functions. So let's get to that, but we will wait until section 2 to discuss these different classes of functions. All right, so this brings us to the end of section 1.1.